Hello fellow skeptics, I'm Luther Name. This is a 20-second video in an arc addressing the topic, is something wrong with physics? What is it, and can it be fixed? Now, the last video that I did, the 21st video, discussed things where I expected to have some pushback. This video was intended to address the further issue of related to can it be fixed, which was to focus on academic physics itself. But in the process of putting together that video, what happened was Sabine Hossenfelder had put together another video that covered many of the same elements that I was going to cover, at least briefly, and she did it better than I was planning to. So I'm not going to duplicate that. What I'm going to do is talk about some other aspects of can it be fixed. And in doing so, originally I delved into how academic physics got to where it was, and it got to be much too long, and I think historically a little on the boring side. So I went back and I've spent some time trying to reformulate what I was going to talk about. Now, one of the things was there's another important element on the pushback that I didn't include in the last video that really needs to be discussed because it probably is the core finding, and there was no pushback, and I expected there to be pushback. So what I'm going to do with this video is delve forward a little bit more on the issue of where I expected pushback, and where I expected pushback was in the determination that the Minkowski reformulation was flawed, in fact entirely incorrect, and to address the issue of where did the Lorentz transforms come from. Now, the Lorentz transform was important because it became a cornerstone in terms of the mathematical underpinnings of what was deemed to be a reliable, correct, or valid equation describing the behavior of objects, physical objects as they moved. And that gave rise to the issue of Lorentz invariance. But as it turns out, the Lorentz transforms are only defined for things moving at the speed of light. Physical objects moving at less than the speed of light, you cannot create a transformation equivalent to the Lorentz transform. Just become the standard Galilean or Euclidean types of transforms that we're all familiar with from mechanics. As a result, the question really is, can the Lorentz transforms have any relevance at all to equations or mathematical descriptions applied to items that are moving less than the speed of light? The other issue was, where did the Lorentz transforms come from? And one of the things I pointed out, as can be seen in this particular view graph, you can see that the Lorentz transforms were identified and found by using this mnemonic, and nobody knows where this mnemonic came from. It just worked, and it was another element of the dabbling that the theoretical physicists do, where they play around with equations. That's not my quote. That's actually from Dirac, who indicated that was one of the things that theoretical physicists do. They play around with equations to see what they get. So there's some issue as to why this particular equation. It's very unusual to have two things equal to zero and then to be compared to one another, and to find a transform that makes one thing that's zero equal to another thing that's equal to zero. This type of equation is not something that is normally used or even thought about in terms of finding equivalencies. But it turns out that you can find a Lorentz transforms. But when you, and using the Lorentz transforms, of course, Einstein in his 1905 paper, in the electrodynamic part of it, where he applied these to the propagation of electromagnetic radiation using the wave equation as a propagating equation, was able to show some interesting phenomenon. He derived what is now considered to be the correct form for the Doppler equation, And of course, as discussed in a prior video, the aberration, where the aberration turns out to have much more importance than has been given by anybody. In fact, it's been mostly misused. So the whole issue is that actually the Lorentz transforms can be found from the electrodynamic part of Einstein's 1905 paper. He simply derived them using the mnemonic and then used them in the electrodynamic part. He never explained how he had derived the mnemonic, and so he dropped that in later years. If you look at the way the Lorentz transforms are used in the electrodynamic part, you can easily see that you don't need to use the mnemonic. You can make the same equivalence using just propagating what's called the complex phase of the propagating wave. The issue is, and the statement is, that you have two observers. You could call one stationary and the other moving relative to the other one, and you look at it and they say they both see a plane wave. Well, what they see is a flux, and I chose to transform the complex phase into a flux of radiation, a flux of photons, and it works the same way, but now it looks more like a conservation equation in both energy and momenta. And what you find out is that you wind up with a linear statement, not the mnemonic itself, but a linear statement. And in fact, you can find a transform between those two that is valid for the mnemonic. And in fact, you don't have to use the mnemonic. You can just use that transform as derived straight from the matching the complex phases of the two propagating waves as seen by two observers moving relative to one another along the line of sight of the propagating wave. The whole issue is that you can find the Lorentz transforms in some other way, and in fact you can show that the a form that you can derive directly from the complex phase in the electrodynamic part of that paper. In fact, you can show where the mnemonic came from, because you can very simply square the complex phase and then set the two complex phases that are squared relative to one another. I always wondered why we always use the square of as a way of doing all of our calculations relative to the so-called relativistic effects that we were detecting. That didn't make sense to me. Why not the linear component? Since nobody was able to actually tell where that mnemonic came from other than it worked, well, then I have an alternative where it works, and now you can tell where it comes from. Now, the problem is that I also claimed that Minkowski faked it. He found another way to solve the equation for the mnemonic, and he derived what was called his 4 vector, which contained time as a 4th dimensional element, and that has since become what's called the Lorentz metric, and that was something that was used in general relativity to find the curvature of space-time, which was part of the metric in defining the geometrical approach to the general relativistic equation. However, when you really look at the Euler-Lagrange equation, which is what Einstein generalized in coming up with his general relativistic equation, you find that that was always a geometric approach to the solution of gravitational problems and to motion in a gravitational field. So I expected to get some pushback on that. Again, it was my own form of mathematical manipulation, but I went back to the source material and found that for some reason people just didn't pick up on the fact that the transform for the complex phase was the same as the transform for the mnemonic, which was derivable from the complex phase. So that was one area. That was another area, and probably and perhaps the most important area that I expected pushback. The pushback, of course, against the Minkowski retransformation was based on that particular observation of the Lorentz transforms and the solution to the mnemonic itself. Now, getting back into the issue of the what's wrong with physics, the whole arc of the prior videos was intended to basically describe what I picked up on in terms of errors and omissions that led us down a particular path. But as you can see, we even got forward into Einstein's time, where his efforts culminated in his relativities. You see that there were some errors right from the very beginning that had nothing initially to do with the idea of there being any sort of error in Newtonian physics. Mainly the way Newton described in the more general sense of the attraction between two objects or two spheres, and the fact that he had reduced one of them to a point mass, and in so doing it forced the equations. Prior video went into more depth in terms of what that is, but what happens is you ultimately can show that if one of the masses is made a point mass with no dimensions, then the other solution is to the problem just gives you the point mass of that particular thing. But what I'm going to do is later, after this video, the next video that I had not intended to put together, that I'll put together, I'm going to address the issue of dark matter and something else that Sabine Hossenfelder reported on just recently, which was the idea of there being gravity in the absence of mass. I don't think that that's true, and I'm going to show you why I think that's not true. In fact, it has to be false, and it's because if you use Newton's general gravitational model, you can show very clearly that where our point mass model, the inverse square model, shows there would be no forces. In fact, his general model shows that there would be forces. If we used the correct equation that Newton had identified as in his Principia Mathematica, then we wouldn't be having some of these inane discussions about dark matter and gravitational forces in the absence of mass. So the issue is, and what I wanted to address, I'm going to do it very briefly, is where modern physics, where modern academic physics has gotten to from a perspective of the organizations and the people that do modern physics. And there's a historical underpinning. And what I'm going to do is I'm going to, in the description, I'm going to give you a couple of references that can help focus on some elements of the sociology associated with academic physics. One of them is a book by Finkbiner called The Jasons. And that'll be important in terms of understanding somewhat the evolution of the not only the behavior but the perception of academic physicists in the post-World War II era. Another book that I would recommend is that by Walter Isaacson called Einstein-His Life and Universe. It's a good read. The physics is bad because he is a reporter and he talked to a variety of physicists, and we all know from my perspective that we've gotten so much wrong, and all the things that Einstein did are basically flawed, and none of the people that he talked to and interviewed for his book were aware of that, probably didn't even care. And so you have to use his book as a way of understanding more about Einstein, the person, and the environment that he was operating in and the people he was interacting with, and not necessarily the science that they did. And Finkbiner's book, in the sense that she was married to an academic physicist, and so when she went through and interviewed various people, she was focusing on some of the historical underpinnings to modern academic physics, which grew out of World War II, and she was looking at some of the events that happened during World War II. The most monumental one that everybody knows about, of course, is the Manhattan Project and the development of the nuclear bomb. She, though, participates in what I call a bit of rewriting of history. A recent movie, well, all of the movies that basically have dealt with the Manhattan Project, but the recent one about Oppenheimer really rewrote history in a way that is inaccurate. Leo Szilard was the guy who came up with the concept of the nuclear bomb because he was an inventor of, and had a patent, I believe, on nuclear reactors. And he envisioned something called a runaway chain reaction, since a chain reaction is the underpinning to how the nuclear reactor works. And so he said if it runs away, you could get an explosion. And so that was the genesis of the whole idea that there might be a bomb that could be made out of these newly discovered materials that fissioned, which meant that they would split apart, and splitting apart they were unstable, and they give off neutrons, and these neutrons then hit other like species and cause them to split, and therefore you had a cascade of atoms splitting and neutrons being released. And of course the splitting created tremendous kinetic energy as well as radiation, and so you had heat. And so that's the core underpinning to the physics in nuclear reactors. And of course it's the true underpinning to an explosion. It just happens faster. In high explosives we have high order, low order, and burning. If you take a chemical explosive, which is atomic, and so that's a true atomic bomb, is a bomb with chemical reactions occurring. You have different ways in which the explosion can occur, and one of them is called high order, which is a very fast detonation wave. You have a low order, which is much slower, less energetic. It's more related halfway between burning and exploding. It has a slow propagation of a shock wave. And then you have burning, and some of these materials you just light them with a match and they burn. What you have is to a certain extent, has been a rewriting of history. And that has covered up to a certain extent some of the things that occurred that caused modern academic physics to take the direction it has. Now that's not the total cause. Other things have happened. In a certain sense, academic physics experienced some of the same things that are occurring now. Everybody, there are a great number of YouTube videos and blogs where people talk about what's wrong with academic physics, and there's plenty wrong, and that's been well covered. But some of the things that have not been mentioned is that you might say there's a bit of deja vu involved. The idea of people not being able to get jobs after getting their degree. Well, there was a time in the 1970 time frame where there are a great number of PhDs in physics who were trained at great time and expense who couldn't get jobs. And as a result, they left the field. And in fact, there had been a lot of that, and it became a cascade after the 1970s. So we've gone through this issue, and other departments other than the physics department within universities have also gone through the issue that they spool up to train people in various areas, various topic areas, various technologies, various science areas, and they're so successful at doing so that these areas basically dry up. They can't take everybody that comes in. And that happened in academic physics. But to a certain extent, and what I'll get into in the next video, I'm going to cut this one short at this point. What I'm going to get into is the evolution of the modern university and what I think may be some of the drivers as to why physics has become, as so many people have now acknowledged, inefficient. Not only inefficient, non-productive, and perhaps stagnant. I'm Luther Name. Leave some comments, and I'll talk to you shortly. I know, quit calling me shortly.